type of motion. It's still in free fall, but instead of having a one-dimensional free fall, it's a two-dimensional free fall. So that's what projectile motion is. Projectile motion is two-dimensional free fall. The reason it's called projectile motion is clearly projectiles, things like missiles and bullets and baseballs. When you toss them or fire them, they go in a very specific motion. And this is the easiest way to think about it. It's not easy, but it's the easiest way to think about it. Because you have two directions, you have to think about the acceleration in both directions. This is kind of hard to do with your brain, to take a motion and split it up into two different directions. This is hard to do. But the idea is that we know what happens to a ball in free fall straight down, in one-dimensional free fall. If I were to draw a diagram of one-dimensional free fall, let's say I hold this up here and I let it go, and I'm taking like snapshots of it every second. Does it speed up or slow down? Yeah. It speeds up. The distance between successive seconds gets bigger or smaller? If it's speeding up, it's got to get bigger. So if I look at a ball, say, that I'm going to drop, and it's at the top, so its speed is 0 here, okay? And specifically the y speed is 0, because we're talking about the y direction. Then it drops a little distance in the first second, a bigger distance in the second, and an even bigger distance, like it's headed off the board, right, in the third second. So this distance is getting bigger and bigger and bigger. That distance is getting bigger and bigger as it goes. Whether I throw something straight up, or whether I throw something in a projectile manner, that still has to be the same. Gravity is affecting it the same way. The Earth doesn't know whether I threw it straight up or threw it in a projectile manner. So if I looked at its height as I throw it, the height is going to look like this, whether it's in 2 dimensions or 1 dimension. Okay? So I know that there's an acceleration in the y direction of negative 9.8 meters per second squared. Negative because we define up as positive. It's because of this downward acceleration that it increases its speed, that it increases its distance as it goes. Now in this direction, so now I'm splitting into this direction. In this direction, there is no gravity. Gravity points down, it doesn't point left or right. So in this direction, there's nothing, we're assuming no air, we always assume no air. There's nothing affecting the motion of the ball in this direction. This is really hard to visualize. The Earth is affecting the ball in this direction. Nothing is affecting the ball in this direction if there's no air. I affected the ball when I threw it, obviously, I made it go that way. But the instant it leaves my hand, I'm not affecting it anymore. The Earth is only affecting it up and down. Nothing is affecting it left and right. So if I were to draw this same picture for this motion, it would actually be successive distances, snapshots. Because in this direction, the acceleration is 0. There's no forces, there's nothing pulling on it, there's no change in speed, the distances are the same at each successive second. That's true for an object that's falling, right? Although this is kind of silly, but the x distance is the same at every instant that it falls. It's 0, right? X distance is 0, x distance is 0, x distance is 0. It's staying the same. If I throw it, I give it some velocity that way from my action, but nothing changes the velocity. If I throw it that way at 100 meters per second, then it's going to have a velocity at 100 meters per second that way. I can't throw it at 100 meters per second. Although if I have surgery, I might have a bionic arm that would be able to. So this is kind of like, you could think about it if you want to, as if I threw a ball in space, where there was no gravitational pull at all, that's what it would look like, right? But that's also the horizontal way of thinking about the ball. On Earth, we have to think about both simultaneously. It has the Earth pulling it this way. It has nothing affecting it this way. So I can think about this as successive snapshots of the same thing. I can think about this, for example, as where it started from. Then the next place it's going to be is there. Okay? It's at the second point on the way up, and it's at the second point on the way over. The third point it's going to be is here. Then it'll reach the top. Then it'll come back down. Then it'll come back down, run out of room. And then it'll be down here somewhere. Okay? So the key to this, and like with my students, I don't know how Dr. Houston teaches, but I make my students draw this on a test for me. I say draw a projectile motion path. What I look for is this spacing changing properly, right? Getting smaller as the ball goes up and bigger as the ball comes down. And is this spacing the same every second? That's what I look for if I ask somebody to draw this picture. So the path that the ball actually follows looks like that. And this is called a projectile motion path. It's parabolic, okay? And what's special about it is that the distance horizontally stays the same, and the distance is vertically increase and decrease in the proper way. And if I'm any good, I can throw this and get it to follow this path. So based on the velocity I throw it at, as to whether it will follow it perfectly, but I'm usually pretty good at this. Let's see if you guys are watching. I can't ever tell if it works. So I did this like completely random sketch. I didn't really think much about it. I just thought about the distance changing in this direction and not changing in this direction. And that's a really good estimate of what the path actually is, even without me being really specific to calculate these distances. Obviously, if I threw it with a bigger velocity, it would end up coming way over here, but I could draw that path too if I took the time to do it, okay? So what we want to think about when we're thinking about problems, so one of the big sets of problems that we do in this chapter is kinematic problems, which you guys should have done to death in one dimension. So a car is traveling this way at 30 meters per second and stops at a red light, and it takes 10 seconds. What was its initial speed and initial position, right? Problems like that. We can now do this for balls, all right? So the way I do these problems is I always think about all the things I need to solve these kinematic problems. So you know equations already. You guys have learned S final equals S initial plus B S initial delta T plus half. Does that look familiar? Typically we just plug X's and BS's. We've learned this one, that BS final is BS initial plus AS delta T. We know BS final squared is BS initial squared plus 2AS S final minus S initial. Are those the only three you learned, or did you learn a fourth? Just these three? Okay. Some books teach a fourth, some professors teach a fourth, but you can do all the problems with these three, so the fourth is unnecessary. So these work in one dimension. They still work in two dimensions. So instead of having three equations for one dimensional, I now have these three in the x direction and these three in the y direction. They all work the same, but I have to do it in the x and I have to do it in the y. The quantities that we end up needing or thinking about, and I always make tables for me, organization. When I was a physics student, I was horrible solving these problems unless I would organize myself. So when I teach this, I always talk about and make a little table. I'm going to run it out of room. AX. I'm going to put a delta T down right there. So, right, I need positions, initial and final positions. I need initial and final velocities. I need an acceleration. I'm going to put a time on the next board. I need a time. In addition, now I need those in the y direction. I've got time. So you're going to see see me writing these tables over and over again in these problems I do. This helps me keep track of what I know, what's given in the problem, and what I already automatically know about everything. So what is one thing I know for sure all the time with every problem we do if we're on Earth? The acceleration of x is 0. What else? Yep, the acceleration of y is negative 9.8. I also know if the acceleration of the x is 0, okay? What's true about these two speeds? You gotta be. And then time is time. If it takes 2 seconds to go up, it must take 2 seconds to go that way, right? So these two have to be the same. So you can really just write that once if you want to, but always just write. So I don't care what problem you do in this chapter ever, right? Even in the other chapters, you could use multiple tables. In the other chapters, all the y values are I'm sorry, all the y, well, depends on whether you do horizontal motion. In horizontal motion, all the y values are 0. In vertical motion, all the x values are 0. But in either case, right, this is true. So I can use this table as a starting point for every problem I do. For every problem I do, I know the x acceleration is 0, the y acceleration is negative 9.8, unless I'm on the moon and they give me some other acceleration. These speeds are the same and the times are the same. So, and I'm going to use these three equations, that guy and those two over there, to solve these problems. So these kinematics, some people are really good at these right off the bat, and some people suck at them. The table tends to help people that don't get it right away. The table tends to help people kind of organize themselves. So let's look at an example from your book. This is number 11, chapter 4. Okay, so number 11 says, a ball is thrown horizontally at 25 meters per second. Travel a horizontal distance of 50 meters before hitting the ground. From what height was the ball thrown? So we've got a ball that's thrown horizontally with some speed. They tell us the speed is 25 meters per second. We know it's thrown at that speed, but it's going to follow a projectile motion path, so it's going to do something like this and hit the ground. They tell us that the horizontal distance that it travels is 50 meters. So again, I don't know Dr. Houston's philosophy, but I'm a real stickler for pictures when I'm teaching this class. And the main reason is because with the picture, the whole problem makes more sense. If you can draw a picture, it's easier to refer to than the problem, and it just makes a lot more sense. The other thing I'm really picky about is a 0 point, is always defining your 0 point, because we have to know the values for these positions, so we have to know where the origin is. So I'm going to pick the origin here. Some people pick their origin up. It doesn't matter where the hell you pick your origin, right? Everybody will have a different origin, potentially, and everybody will get the same answer. But you have to have your origin and be consistent with it. I think this is probably the place most people would pick. So these values tell me certain things, right? I have an initial velocity. Is that an x velocity or a y velocity? It's an x. So this is the initial x for my table. I don't know how high it is. In fact, that's the question, the big question that the problem is asking. What is that? So I can automatically fill in that velocity into my table. I also know that if I put my origin here, I know that the initial x is 0, right? So this is x initial. And I know that it goes 50 meters, so this is x final. And I can plug those into my table. So let's do that real quick. I've got an x initial of 0, x final of 50, v initial of 25. I automatically know that that's also the final velocity in the x because I have this table that I write down. I don't even have to think about it, although you should know that just right. And I don't know the time, so that's the one thing on the left side of the table that I don't know. Do I know anything on the right side of the table other than the acceleration? I know one thing, two things. Vy final is 0, absolutely, I'm sorry, y final is 0, because it hits the ground. Okay, hits ground. What else? Vy initial is 0. Starts horizontally. So because it starts horizontally, there's no vertical velocity. Now the instant after I throw it, there is going to be vertical velocity, right? It immediately starts to fall down. But that instant that it's thrown, the vertical velocity is essentially 0. One mistake I see students making a lot is because it hits the ground, they want the final velocity to be 0, but that's not true, right? Because we're always in the air, it's always the instant before it hits the ground. And this is what they're asking for. So I have a lot of information on the left side. I don't have hardly any information on the right side, but there's a link between the two sides, which is the time. The time links the x side to the y side. So I can find time on the x side, right, because I know everything else but time, and then I can bring it over here, and I'm going to be able to find the other thing. So let's look at that real quick. I always tell my students that if you can't figure out how to start these problems, just start plugging into the equations. We have these 3 equations. If you don't know which one to use, just start plugging into them, and eventually you'll find it. Okay? Don't always think it's hard. Most people want to be able to solve the problem in their head before they start writing on a piece of paper, and that is not possible usually with physics. So some people can look at the equations and know immediately which one to do. I would use this one. Maybe, let's see. X. Look at X. So this is the first one that pops into my mind to use because I need time, and this is the one that has time as a single thing, right? The problem with this is that I'm going to plug in my values. I get 0 equals 0 plus 0 times time. Not 0. Like that. True, right? Incredibly long. Okay. So this is one of these things where it works, it's true, it didn't help me find the time. The other equation I have that has time in it is x final equals x initial plus vx initial delta t plus half ax delta t squared. So I'm going to plug in, I've changed the s's to x's because I'm working in the horizontal direction at the moment. So my final x is 50, my initial is 0, my initial speed is 25, I don't know the time, and my acceleration, the x is 0. The x direction is really easy in projectile motion because a whole lot of stuff is 0. The accelerations are always 0. So this is solvable for the time. And when I do it, I get a time of 2 seconds. That didn't answer the question. The question asked for the height, but I have to find the time before I can figure out the height. So now I come over into the vertical column, where I've got a time down here of 2 seconds. I know these 2 values, and this value, I'm missing 2 values in the y table. And the way that this works is if you're missing 2 values in the y table,